Greetings, ladies and gentlemen. My name is Ryan Shazani and welcome back to another physics video. In today's video, I'll be going through how to find the electric field due to an infinite surface. So we'll be given a point P, which is distance x above the infinite surface, and we're trying to find the electric field at point P. So there are two approaches to this question. The first approach is by utilizing Gauss's law, or one of Maxwell's equations, which is the closed surface integral of the electric field dot A equals to the total charge enclosed by it, or by the Gaussian surface over epsilon naught. And the second method I'll be using is by finding or integrating dq over 4 pi epsilon naught r squared. So I'll be showing how to use the first method first, which is by utilizing one of Maxwell's equations, and then I'll be going through the second method. So let's start. So we'll be drawing another diagram because I have to show you the Gaussian surface, or the enclosed surface. So this is a closed surface, or a Gaussian surface, and this is point P, and point P is distance x away from the infinite surface. So let's start writing down the expression for Gauss's law. And how are we going to write that down? We actually have to consider that there are two kinds of surfaces here. The first is the flat surface, okay? And the second is actually the curved surface, because it is a cylinder, right? So this is the curved surface. So it's simply just the closed surface integral of the flat surface plus the closed surface integral of the curved surface. And this is equal to total charge enclosed by it. So what is the total charge? The total charge is just here on the surface, and we'll call this area A. So sigma A over epsilon naught. Now let's take a look at this. The electric field will be coming out like this, and it is actually parallel to the curved surface. So we can write down, since the electric field is parallel to the curved surface, then the electric flux due to the curved surface will be equals to 0. Therefore, the closed surface integral of the curved surface is equals to 0. And simply this is just equals to the flat surface, the closed surface integral of the flat surface dot dA plus 0 equals to sigma A over epsilon naught. Now, because the electric field at the surfaces are all equal in magnitude, therefore I can just make this into a scalar quantity, and I can write down as E equal to sigma A over epsilon naught. Now, what is the area here? There are actually two areas, because the electric field is cutting two flat surfaces, which is first here and second here. So we can just write it down as E bracket 2A sigma A over epsilon naught. Why A? Because A here is equals to the surface area here too. So E at point P, or electric field at point P, is just equals to sigma over 2 epsilon naught. And voila, this is the answer to the question. So this is the first method by utilizing Gauss's law. The second method I'll be showing you right now. So the second method is by using the normal equation for electric field. So E is equal to integral of dq over 4 pi epsilon naught and some distance squared. Okay? So the method that we'll be approaching, or the method that we'll be using, is actually to find the electric field due to one ring. So we'll find the expression of electric field due to E ring, and then after that we'll integrate it from ring equals to 0 radius to ring equals to infinite radius. So from E ring to E surface. So this is the method. So let's start writing down the expression for electric field due to one ring. So the distance is actually here. So we'll see that the radius of the ring is denoted by r, and therefore the distance between point P and the ring is equals to square root of x squared plus r squared. Okay, now what does dq represent? dq, if we were to take a look at this ring, dq is just one point at the ring, so it's just a point charge. And how are we going to find dq? dq is simply equals to the area charge density, sigma, times the arc length of this. So if this is d theta and this is r, then this is just r d theta. Okay, and next I'll also get the thickness of this ring, which is dr. Why dr and d theta? Because it is a area charge density, so we need the units to be meters squared. Okay, so next we'll just substitute this in. So this is just sigma r d theta dr. But if we take a look at this, we also have to consider that at this point the electric field will look like this, and at this point will look like this, and the horizontal components of it would actually cancel out. So we just have to consider the vertical components of the electric field due to the ring. So we'll just add a cosine theta behind. Actually, this is not cosine theta, this is cosine, let's say cosine lambda. So this is lambda. Okay? Alright, so next, what we're going to do is we're actually just going to integrate it from, in terms of d theta, or with respect to d theta, from 0 to 2 pi, because we're trying to find from this point charge to all the way to here. Okay, so we can simplify this even further actually. Cosine lambda is basically just equals to x over square root of x squared plus r squared. And this is just integral sigma r dr over 4 pi epsilon naught x squared plus r squared of 3 over 2 d theta. And because there are no theta inside this expression, then it will just be equals to sigma r dr over 4 pi epsilon naught x squared plus r squared of 3 over 2 times 2 pi. And this just gives us sigma r dr over epsilon naught x squared plus r squared of 3 over 2 and over 2. Alright, so we have the expression for electric field of one ring. So now we're just going to find the electric field due to the whole surface, which is actually quite simple. So I'm going to erase all of this. So electric field due to the surface is then just the integral of this whole thing, sigma r dr over 2 epsilon naught x squared plus r squared for 3 over 2. And we'll be integrating it with respect to dr. So we'll take from radius equals to 0 to radius equals to infinity. And this is just the integral of r over x squared plus r squared or 3 over 2 dr. So how are we going to solve this? So simply, let's just write it down separately here. So r x squared plus r squared or 3 over 2 dr is equals to, so let u equals to x squared plus r squared. So du is then equals to 2r dr. And if we take a look at this, we have r dr. So r dr is equals to du over 2, then substitute this in, will be equals to du over 2, and this is just u of 3 over 2. Okay, so this is just equals to integral of half u for negative 3 over 2 du, and this is just u for negative half over negative half and plus c. Okay, so this is just negative u of 1 over 2 plus c. So then we'll just substitute this in, sigma 2 epsilon naught negative u, and u is just x squared plus r squared. So 1 over x squared plus r squared of half from 0 to infinity, and they'll just give us negative 1 over x squared is a constant, then plus infinity minus 1 over square root of x squared plus 0. And this will give us sigma 2 epsilon naught minus 0 plus 1 over x. And we're actually missing something here. We are missing an x here. So this just gives us sigma over 2 epsilon naught. Electric field at point P is equals to sigma over 2 epsilon naught. So voila, this is the answer to the question. If you found this video helpful, then subscribe to my channel, like the video, and share the video. And I'll see you in the next video. Thank you for watching. Goodbye.